Okay, now we're going to do different kinds of functions than the ones we've seen in previous videos. The functions we've done this far are of domain, real numbers, and then the range is the three-dimensional space. Um, so that means that here we can represent the domain with one line, and then so these are the inputs, and then the outputs are in the X, Y, Z space. And we cannot really represent this with one picture. I mean, we can see what happens, the motion here that happens in space, but the time cannot be really described in the same picture unless you just say, time equals 0, time equals 2, and so forth. If you actually describe the times, then you can, but as a part of a point, we cannot really put the time into this picture because we would need four dimensions, and I cannot draw 4 dimensions. If you can draw 4 dimensions, let me know how you do it, because I cannot. So we just talk about this, and in the background we realize that this is the input. Okay, so this is one input. We're going to do problems where we start with 2 inputs and we end up with a single output. So the domain would be the plane. By the way, back here, if we have a point on the domain, then that point corresponds to a point on the range, on the graph. Here, if we have a point on the domain, which would be an XY point, that point would correspond to a range somewhere in here, a point on the range, rather, in the range. Okay, but now we have 3 dimensions. In this example from previous videos and previous sections, this is 1 plus 3 dimensions, that's 4 dimensions. We cannot draw that in one picture, but here we got 2 dimensions and 1 more, so that is 3 dimensions. We could put this together into one function, into one graph, rather. It is a function, both are functions, but here we could consolidate this into one graph. And the way we do that is by drawing the domain on the floor, X, Y, and then Z would be the range. So this input, so let's say there's an input here, an X, Y value, which will correspond to a Z value up here. And then we can have perhaps another different Z value there. So then, and this doesn't have to be nice and straight. And then perhaps back here, we could have another Z value there. And then maybe a point back there has another Z value here. And then we connect those. And we don't know in advance, without knowing the nature of the function, whether it's quadratics, trigonometric, and some other kinds of functions like exponential. We don't know the shape of this. This could be straight for all we know, or but we have some kind of sheet that is floating up here in the space, and we think of this as the domain being 2 inputs, X, Y, and the output is the Z value corresponding to those. Yeah. A similar thing happens in 2 dimensions. I'm going to try to squeeze that in this page here in 2D, because I don't want to make too much of a big deal. If you have a function y equals f of x, technically speaking, you got 1-dimensional input, 1-dimensional output, but we consolidate into one picture where we have the inputs and the outputs. So for every x value, so there's the x value, we have a corresponding y value. Back here, for every xy value, we have a corresponding z value. Say this one, we have this z value. One thing I want to clarify is that we think of xy as one input. So again, the 2 numbers x, y make up one input. Uh, I guess we could, it could be a little ambiguous. Somebody could say, wait a minute, that's two inputs. Sure, we can think of it as two inputs, or the pair is one input. Um, yeah, so two inputs make up one pair, and we think of the pair as um, the single input. Let's do a whole bunch of examples. Yep. So let's start with a simple one. F of xy, which is going to be also z. If this is an example, 5, the output is 5. What does that mean? If you enter any input, 1, 2 is one input, one pair made up by two numbers. Some people will say, wait a minute, that is two inputs. Fine, whichever way. I think of one pair or two inputs. Yeah. So if this is given this as initial function, the output is going to be 5, because that's what it says here, 5. F of 3, 7 is going to be 5. F of 13 pi, the output is going to be 5. F of 0, negative 1,000, the output is going to be 5. So no matter what the input is as a pair, or inputs are as individuals, the output is going to be 5. So that is the constant function, because no matter what the input is, you get the same constant output, which is, in this case, 5. So what is the graph of that? Well, for every input, you get the same output. So the outputs are going to be leveled at a height of 5. So where that intersects, this is going to be 5. And everywhere, for every input, you're going to have an output of 5, no matter what. Yeah, this is an important example. Don't confuse it with 5x, for example. That would be a completely different kind of graph. So this is a constant function, and it's just a horizontal plane when we graph it in the x, y, z three-dimensional coordinate. Example 2. Let's say we have a plane that goes through this point, and that point. So pretend this is 2, 0, 0, 0, 3, 0, and 0, 0, 5. So that is a plane. By the way, this plane extends farther beyond this octant. I'm just showing here the intersections with the x, y, and z axis. But there is more to it. The graph continues as you extend this plane in that direction, in this direction, and down here, and everywhere where it can be extended. So this is a plane. How do we come up with the equation of this plane? This is from previous subjects we have covered, but let's review it. So I want to have coefficients of x, y, and plus coefficient z, so that at some points we're going to get 2 or 3 or 5. I want to be able to obtain 2 or 3 or 5, and the number that contains 2, 3, and 5 as factors is 30, because 2 times 3 is 6, times 5 is 30. So this will allow me to get 2, 3, or 5, depending on what I want to divide by. So if I want to get a 5, where those two guys are 0, so what we can do is just pretend that is not there. So how do I get z equal to 5? Well, we have to divide by 6. If we divide by 6, if those two numbers are 0, if x and y is 0, pretend they're not even there. So if x and y are 0, so that whatever the coefficients we have here, say 45 and 17, if you put 0 here and 0 here, that's going to be 0 anyway. So it won't matter what those coefficients are. If you put log 0 for x and 0 for y, 6z will allow me to have 5 for z, because 6 times 5 is 30. Okay, now we do the same thing with, say, this point. We want 3 out. So I want 3 when those two guys are 0. So pretend that, oops, that and that is 0. So pretend that they're not even there. So what number times y gives me 30? And of course, that is, no. What number times 3 gives us 30? There we go. And we need a 10. So when z is 0 and when x is 0, this coefficient, this term will turn out to be 0, and so will this. Even though we don't know what that number is, since x will be 0, the whole product will be 0. So 10y equals 30, which means y will be 3 when x and z are 0. And then we do the same thing for this. For the coefficient of x, we need a 15. So there's the equation, yeah, because 15 times 2 gives us 30 when those two are 0. So there we have it. That is the equation of the plane that goes through 2, 0, 0, 0, 3, 0, 0, 0, 5. That's a neat way to obtain that equation without too much drama. Now, if we solve this equation for z, z will be equal to 30 minus 15x minus 10y, but then we have to divide by 6. And typically we rewrite this as a, there's a couple different ways to write it, but typically we rewrite this as terms. So 30 divided by 6 is 5 minus 15 divided by 6, but we simplify that. If we simplify 3's, we end up with 5 divided by 2x. 10 divided by 6 is again 5 divided by, simplify the 2, so we end up with 3y. So if z is written this way, we have exactly the same plane, but now we can think of this as f of x, y. So this is the function, this is the equation of the plane that goes through those 3 different points. So 5 is the z-intercept. Remember when we have a straight line in 2D, we have the y-intercept. Well, this is the z-intercept. I guess one way to think of it, alternatively, equals z equals, there's a slope of -5/2 on the x direction. So if you go in the x direction, this is sloping down at -5/2. There's a slope of -5/3. And it makes sense, by the way, that we are sloping down by 5/2 because the run here is 2 and the rise is 5, except that we're going backwards. And so that's why this is going down. So run 2, drop 5. So rise over run. Same thing as with 2D. And then we have the z-intercept, which would be just the number 5. There we go. So this is another way to express. This is an extension of expressing a straight line, except that this is a plane. That was example number 2. Example number 3. Okay, so you guys are familiar with x squared plus y squared plus z squared equals 25. This is the equation of blank. I'm laughing because I don't like to do videos where I don't finish the sentence, assuming that the viewer is going to finish the sentence, because that is too much like a Dora the Explorer video. I don't know if you remember those videos, children videos, where they're waiting for the audience to give the answer. So I'm not going to do that. I was just joking. Anyway, this is a sphere. We know that is a sphere with center at the origin, and the radius of the sphere is 5. So this is a sphere. It goes up like that, and then it goes around this way, and the radius is 5. So this point, for instance, let's see where, well, let's put this one here. It's probably a little clearer. That point is going to be 0, 5, 0. And then we have a sphere, totally round, with an equator up here, a North Pole, a South Pole, The South Pole is going to be down there. All right. So as with the previous example, example 2, remember, um, there it is. We started out with a plane, and then we solved for z, and that gave us the equation of the function. Similarly, here we can solve for z and obtain the equation of the function. So z, in this case, will be, we got to take the square root after moving the x squared and the y squared to the other side of the equation. Now, when we take the square root, we are going to end up with a plus and a minus. 25 minus x squared minus y squared. That is actually 2 functions. It's not 1, it is 2 functions. Yeah. One for the upper hemisphere and the other one for the lower hemisphere. Yeah. So we have f1 of xy, which would be the square root of 25 minus x squared minus y squared, and that is half of the sphere. So just half of it, no more, no less, just half. Yep. And then f2 xy, which would be the opposite of this one, 25 minus x squared minus y squared. And that's going to be, let's do the circle first, and then that would be the bottom. So that is the bottom, that is the top, bottom. By the way, you don't have to solve for z, you can solve for y, but then your picture is going to be sideways. It's going to be drawn sideways instead of right side up with a z on the top. So be aware, oftentimes I give problems where there is a little bit of ambiguity. Z equals the square root of 25 minus x squared minus y squared. But it is clear in this context that the z has to be positive. So in this equation, z must be positive. Why? Because there is no negative. The square root by itself represents the positive square root of the number. Yep. Yep. So this is example 3. Example 4. There's many examples we have to become familiar with. So start up with z equals the square root of 25 minus x squared minus y squared. And you're going to say, wait, didn't we just do that? No. Well, yes, but we're going to add domain. So comma, x is greater than 0 or equal to 0, y is greater than or equal to 0, implies that we are only going to take values that fulfill this requirement, the extra requirement. So that means we're going to have just 1/8 of the sphere. So just the part that is in the first octant. So this is the only part there of the sphere that will be represented by this function. Again, this is the same as this example, example 3. If you, yeah, we can just look at this part, which is the upper half. But if we add this domain, then we're restricting how much it is. So this is all of the upper half of the sphere, just the top of the sphere. And now we got 1/8 of it. So if you take an orange and then you split it up into 8 pieces by halving and halving and halving, then we are going to end up with this 1/8. Okay, example 5. Z, which again, f of x, y. I neglected to put f of x, y here, but it is understood the way it is written. Same thing, 25 minus x squared minus y squared. But now let's change the domain. Let's say the x's can go from -1 to 1, and so can the y. So can do the y's. Okay. So we have a different portion of the sphere. So we have a 2 by 2 square. That's the domain, because we go from -1 to 1 on the x-axis, from -1 to 1 on the y-axis, and all the points in between. And so when we go up, we're going to end up with a portion of the sphere like that. So yeah, so it is the top of the sphere, but it is cut in such a way that this is straight. So the top view is going to look like a square. A three-dimensional view, in a three-dimensional view, we can still see the curve of the sphere. So we still have the sphere. We have some on the first octant, some on the second octant, third and fourth. Yep. So we have this surface. Yeah, the top of the sphere. Yep. So pay attention to the domain of the function, because that can change how the picture looks like. Let's squeeze in here example 6. I'm going to draw a line there. So what if f of x, y is equal to x squared plus y squared? This is a good studying example to show a new idea. So this is a parabola, no matter how you put it. Let me draw the picture first. So we got, notice that if you look at x squared plus y squared equals a number, a fixed number, that is going to give us a circle. Let's say the number is 16. So that will give us a circle of radius 4. So a radius 4 circle will have a level of 16. Remember, the output is z. So the output will be 16 on a circle of radius 4. On a circle of radius 3, the output would be 9. So kind of down here, we're going to have a radius 3. Pretend that is a nice perfect circle. My circle is not very even, but that will have an output of 9. And then when you have a circle of radius 2, we will have an output of 4 when the radius is 2. And then when the radius is 1, we will have an output of 1. So by putting together this as smoothly as we can, we're going to end up with this kind of surface. So this is the surface we come up with. And that surface is called paraboloid. We have seen this before in one of the previous videos. This corresponds to z equals x squared plus y squared. So that is a regular paraboloid, a circular paraboloid, because the cross sections are going to be circles. Now, and this extends farther, of course, that goes up. These cross sections are called level curves. Yeah. So the cross sections are called level curves. And they are very important. They facilitate the understanding of how a surface looks like. So for instance, we have a level curve map of this. Okay, so level curves map, or level curve map. And that tells us that there's a point at 0. At 1, we have this circle. At 2, we have a bigger circle. No, that's 4. Oops. So the output, this is 0. The output is 0 here. Output is 1. Output is 4. Output is 9. Output is 16. And that tells us that this is the bottom, 0. And then as we move up, this increases. So by looking at this, we can visualize what a three-dimensional surface this is. Again, because at a level of 0, you got nothing, use a point, and then you got a circle at level 1. At level 4, you got a bigger circle. At level 9, which is farther up, a bigger circle, and so forth. And that gives us, and then there is corresponding in between circles, We only show a few of them, but that gives us the paraboloid. So we're still in the same example. This is z equals x squared plus y squared. And what I'm trying to do is show how the level curves look like. So let me talk a little more about level curves. Let's make this as an example in its own. Example 7. Okay, so let's say you have a surface like this. So there's a surface like a hill, a little mountain. All right, so it's very steep if you go up this way, but if you come this way, it is not as steep. So let's say this level is 0. This is 1, whatever you want to call it, 1 meter, and then 2 meters, 3 meters, say 4 meters. So this is, I'm trying to show you a 3-dimensional picture. So pretend this is a 3-dimensional picture. This is in 3D. We can draw and pretend this is reasonably smooth all around. So we can draw the level curves corresponding to this mountain by, okay, so here we have a fairly large, so this corresponds to level 0, there. Then we have to move to level 1. Now notice that from here to here, there is a long distance, while from here to here, there's a shorter distance than from here to here. So this is still level 1, and this is level 0. But again, from here, from this distance to this distance, we got a shorter, and from here to here, we got a longer distance. So this could be the level 1. Level 2, again, the distance from 1 to 2 on the left is shorter than from 1 to 2 on the right. 3, so that is 2. Same kind of situation. So if you see level lines that are close together, I'm going to exaggerate. I'm going to do another example. But the idea I want to show you is that if you see level curves that are close together versus level curves that are farther apart, that tells us how steep the graph is going. So let's do another level curve example. So this would be example 8. So this is more level curves. Let's say I give you, or I show you this, and then one that is close here, but farther, close here and farther, close, farther, close, farther. Okay, so let's say this is one more. Okay, so this is 0, 1, 2, 3, 4, 5. Okay, so this is a map of level curves. Yeah, 0. So that means that we're going to have a mountain that is going to go up to 5, maybe a little more because we don't have a dot where it ends, but at least 5. And it looks like it is going to be very steep here, and here the slope is very gentle because it takes only this much distance to go from 0 to 5. So we're going to have this distance, very short distance to go from 0 to 5. Then maybe a little tip here. And then it is going to take, again, this is still 5. This circle represents a level 5. So this is a level 5 and then level 0. And it takes this much distance to go from 5 to 0. So again, this is 0, and then those are the level curves, 1, 2, 3, 4, 5. Yeah. And then, of course, the sides we cannot quite see here because, yeah, this is supposed to be also pretty steep, pretty steep. Here's the gentlest way to go. Yeah. So it's neat to see all of these different uh, examples. Example 9. Okay, let's say you have f of x y equals x squared plus 4y squared. In this case, the cross sections are going to be ellipses, and this 4 indicates that we're going to be steeper going in the y direction. So going in the y direction, we have a much steeper slope than on the x direction. So steeper on the y direction. So that means that the level curves are going to be ellipses that are going to go about this way. So they're going to be long on the x, shorter on the y, on the y's. Again, long, short, and this pattern will continue. And then as we join this, we're going to have the same kind of ellipsoid. No, I'm sorry, not ellipsoid, paraboloid, where the cross sections are ellipses. Yes, so again, on the y direction, so going this way, this is going to be steeper. Going on the x direction, we're going to have a normal steepness to it. And this continues on. Let me try to draw a nicer picture. So we have there, that's probably a little nicer. There we go. So we have, and there is the center. This is an elliptic paraboloid. So it looks like a parabola, but the cross sections are elliptic. That's the elliptic paraboloid. Yep. So become familiar with those kind of examples. There are many, many examples. The one you definitely want to not neglect is planes. Example 10. Okay, let's say you have f of x, y equals x plus 2y plus 3. Yep. So one way to address this is to go back, put a z in here, and then figure out what the x-intercepts are, and then just draw it as a plane, as we did with example number 2. Yeah, but going backwards, if you have this, then you can come up with the intersection points, and then you can draw your picture. So that's one way to go about it. Another way to draw this linear function is to figure out the level curve. So the level curves here would go probably this way. Notice that all of these points are going to be about the same height. All of those points are going to be, for instance, this is 0. This may be 2, 1, and this is 2, maybe 3, 4, and then 5 will be here. But actually, the plane keeps going. So, and then maybe 6 and so forth. So the level curves of planes are going to be straight lines, as opposed to level curves of things that are not planes are not going to be straight lines. So just be aware that if you have a level curve map and all of them happen to be straight lines that are parallel, they have to be parallel, by the way, otherwise it doesn't work either. Then we have a plane. So let's see. Let's solve this equation for y. Well, actually, let's fix this to 5. I'm just arbitrarily fixing x plus 2y plus 3 equals 5. So 5 is just a random number. I say that 5 is one of my favorite numbers because when I was a child, I used to watch Speed Racer, and that was his car number. All right. So just a random number, 5. If we solve this equation for y, let's see. So the 3 goes over, so we have 2. And then the x goes over, but then we got to divide. So by 2, so negative 1/2 x plus 2. Solving this equation for y, we end up with this line. I'm going to start drawing this. Okay, so the slope is negative 1/2, but we have a y-intercept of 2. So we have something like this. Okay, so this is 5. This graph will be 5 on these inputs, all of those inputs, starting with 2 and then going down this way. Okay. Pick another random number, say 4. X plus 2y plus 3. So that is the original function. Make it equal to 4. And again, that is just a random number. Because I want to know which way this is going. Are we going to get 4 here or 4 there? Rather, 4 here or 4 there. We don't know which way. We know that this line gives us a constant of 5 on the output. And because we have a straight line, rather a straight plane, we're going to have 4 either here or there. Let's see. So let's solve this equation for y. Y will be equal to, let's move the 3. So plus 1 is the y-intercept. Negative 1 over 2x. So we have the same slope. Plus 1. So we're going to have the same slope. So this is going to be a level curve 4. Let's do one more. But I think we can figure out the pattern almost at this point. But let's do one more anyway. X plus 2y plus 3 equals 3. And of course, y is going to be negative half x. That's pretty clear because the 3 is simplified. So this line is going to be 3. Level curve for 3. And then we have a clear pattern. 2, 1, 0, negative 1, and so forth. And over here, we're going to have 6. So this is telling us that we're going to have a plane. This is a top view of the plane. So, and here we have a level 5. As we move this way, we're going to have bigger numbers. As we move this way, we go down to smaller numbers. I haven't drawn this before. So let's see. The lines are going to be positive. So this is 1 and 2. 1 and 2. Oh, okay. So this is going to be a 4, about a 4. But then they're going to get bigger. 5, 6. Oh, okay. And then they get smaller. Actually, they go into that corner without touching this yet. So yeah, there you go. It's something like this. It vanishes behind this axis, and then they continue behind. This intercept is not the origin, by the way. Where do we cross? At 3. Let me draw a newer picture. Scratch this, scratch that. A new picture, now that I have more information. So at level 3, yeah, there we go. At level 3, the plane is going this way, down this way. And those lines correspond to lines down here. But never mind those. This is the actual plane that is going on. And then at 3, we have this. And then if you want to go lower, then you have to go behind this z-axis to see it. Practice this. It takes a little bit of practice to develop an intuition about this kind of surfaces. There's one more example I want to show you, or one more idea. So far in this video, we've done functions that go from r squared into r. We could do functions that go from r cubed into r, but that is not drawable. It is not as easy to draw anymore because we're taking 3 dimensions, x, y, z, and putting it into 1 dimension. So again, we have the problem that in total we have 4 dimensions. So how do we draw that Yeah, for every point here, we have a corresponding point out there. To be honest, what I try to do is do what I call flying with only instruments, which means um, I kind of trust what's going on based on these examples. And the same kind of thing will happen or very similar on these examples. But even though I don't quite visualize them completely, I trust that the same thing is going to happen or very similar things will happen. And I'm okay with that. I'm okay with not trying to draw 4 dimensions. I just made peace with that. I'm okay with that. I call it working on 4 dimensions in mathematics is what I call personally um, flying with instruments only. So you don't see what's going on out there. You're just trusting that the instruments will guide you through your flight. All right, we'll stop here for this video.